Anybody have an answer? You can feel free to share it.
0.2698.
Yep, I'm getting the same thing. Let's say that it is approximately, so we'll use the squiggly equals. I think the first time I ever saw the squiggly equals, I just thought that the instructor was trying to be clever and funny, but this is actually a mathematical symbol. I mean, it lets the person know that we are now going to round. We're going to lose some precision here. So I'm going to say 0.26, and how far we go is really up to us. Let's go 9, whatever. We could say 0.27, doesn't matter. Is that all right with you? That's it, that's the answer. That is the slope of the tangent line. So that wire, here's the pole. At that point where the wire comes in, like this, the slope of that line is 0.269, which means that it's a positive number, right? Which means that we have a little bit of an angle like this. But it's not much of an angle, is it? Right? Slope of 1 is 45 degrees. So 0.269, that's, so this wire is stretched out pretty good, isn't it? We've answered the first part, part A. Now,
That's the slope of the tangent line
at that point. Yep. Out of curiosity, what would be the slope of the tangent line at the bottom of the catenary? Should be 0. So how can we verify that? We just take the derivative and plug in what for x? 0. Sine hyperbolic of 0 would mean that we replace this with 0, and that with 0, and that with 0. And you get e to the 0, which is 1, minus e to the 0, which is 1. 1 minus 1 is 0. So it does match up that it would work. All right, so we've answered the first question, yes? The second question is to find the angle.
So that's measured in what? 0.269 is saying?
It's just the slope. So what is that? That's your ratio of rise over run. That's what that is. There's not a unit measure for it. That's why for part B, I'm actually going to ask you for the angle. Okay? So for part B, find angle between wire and pole. So this is what I mean. Here's the pole. Here's the wire coming in. And what we're imagining is that tangent line that's coming through here. We found the slope of that tangent line, right? And what we would like to find now is the angle right there between the wire and the pole, which would be, let's call theta. That's what I'd like to know. Make sense? So how could we find the angle? I'm going to move that theta. Here's theta right here. How could we find that angle? There's no calculus involved with this step. You just have to think through things. So what does this mean again? This is slope, right? This is slope. This is the same as the rise over the run of that tangent line, isn't it? It's the rise over the run. So you could look at it as 0.269 over 1 if you wanted to, couldn't you? And so if I come back to this right here, I could imagine drawing a triangle like this. And if I pick any arbitrary point here, and then this point right here, I know that the ratio of rise over run is that, yes? So if I look at this triangle, kind of exaggerate a little bit, I am trying to find theta, which is up here, and the rise, right? This should be what, according to this over here? 0.269, and the run should be 1. So in terms of theta, I have the opposite side and the adjacent side of this triangle, don't I? In terms of theta. So what trig function from pre-cal would connect those two? We'll connect all these three together. Tangent, right? So I know that tangent theta should be equal to opposite over adjacent. You'll realize because theta's up here, this is opposite and that's adjacent, right? Okay, so 0.269. And so then how would we get theta from that? Yep, inverse. We take the arctan on both sides. So if I take arctan on the left, it kills off tan. And if I take arctan on the right, well, then I need to get my calculator out and do that. And let's see what answers we get. .3 theta is approximately 1.3. Anyone get something else? I got 74.9. That's right. So, who else got 74.9? Anyone else? Everybody's in radian mode on their calculator? Wow, okay. So, or 74.9 degrees. So if I don't put the unit here, it's understood to be radians. Right? Remember that from pre-cal? Like if you see a number that represents an angle, that is in radians unless it is specified that it's in degrees. The only way you can specify it's in degrees is by putting the degree symbol. So this angle, the angle that that opens at, right? The angle that that's meeting, where the wire's coming in, it's almost like if you could go in there like zoom in, zoom in, zoom in, zoom in, zoom in, and get way up into that corner and get like this infinitesimal little triangle in there, that angle would be 74.9 degrees. So either one of these answers would be valid. Make sense? Okay.
With arctan, like any of the arc ones, there's like the domain restrictions.
Mm-hmm.
Could we have gotten any sort of like data that would have been outside of the domain restrictions?
Well, arctangent doesn't have a domain restriction. Arctangent doesn't. The domain of arctangent is negative infinity to infinity. And that comes from, if you look back at tangent, this is tangent, right? Tan, x. So the range of this is everything, right? So that means the domain of its inverse is everything. It's only with the arc sine and the arc cosine where you have restrictions. Yeah. So it's good that you're thinking that, but we get lucky here because we're using arctan and that doesn't matter. All right. You good? Let's see. I'm going to do one more problem, and then I think I'm going to give you, maybe if we have a little time, some time to practice taking some derivatives, because really, when it comes down to the homework for this section, all you're going to do in your homework is, in the beginning of the homework, I'm going to ask you to do like find sine hyperbolic of 0. So all you have to do is like plug 0 into the formula and get the answer. Kind of like what we just did when we plugged in 8 over 30. So you practice doing that. Then the second part is to prove some identities. So you got to go through and like mess with the algebra and prove some identities. The next part is start taking some derivatives of these inverse hyperbolic functions. So you use the formulas, you use everything you know about product rule, chain rule, quotient rule, and you grind out some derivatives. And then the last problem for this section is one of those pole problems, just like I did. The next problem is not in your homework, but it is a problem that I like to do. All right, so I'm actually working number 48 on page 190. If you're following along, you don't need your book. But let me write down what's here, and then we'll talk about it. I'll read. Using principles from physics, it can be shown when a cable is hung between two poles, it takes the shape of a curve y equals f of x, which is catenary, all right? And that curve must satisfy this equation. Here, rho is the linear density of the cable. So you have, cables have different densities, how much mass is there. So this is the linear density. G is gravity. Okay, so that's a constant as long as we're on Earth. And pretty much if you're hanging cables, I'm pretty sure you're going to be on Earth, right? But this formula works for any planet, so that's good. And then T is the tension in the cable. All right? So I like to show this problem because it's the first time usually that students have seen what's called a differential equation. It is an equation, right? It is an equation that involves the derivative of a function. Yeah? I'll give you an example of a differential equation, a more simple one. All right, let's do this. Y prime equals y double prime. That is called a differential equation. Can somebody tell me what y has to be? E to the x. Would that satisfy this? Is the derivative of this equal to its second derivative? Yes. Is this the only answer? There's one more. Y is 0. Or you could say y is what? Any constant. Because the derivative of a constant would be 0, and the second derivative of that would still be. But we call this the trivial solution because it's boring, right? So this is an example of a differential equation. This is an example of a differential equation also. It's a little more complicated, right? So all of this problem, all they want you to do here, do y'all understand what this means? That means the second derivative. Okay, so we know, that y prime is dy dx, right? That's another notation. And y double prime, the way we write it is like that. D squared y over dx squared, like that. That's the way we write the second derivative. And then what is this? The first derivative squared, right? That's what this is. So this differential equation is really saying something like this. Y double prime equals some constant over constant square root of 1 plus y prime squared. So it's a lot more complicated than that one I just put up here, right? So what's the solution to this? Well, in physics we can show that a wire hanging has to satisfy this equation. All right? The only way you can have a wire hang in that shape is if you can find the solution to this. Now don't ask how we get there, but that's what we're searching for. So with the y prime equals y double prime that I put on the board here, we got that solution just by thinking and inspection, right? So e to the x works. What works here? Well, you take a class called Differential Equations and you learn how to find the solutions to this. I'm going to give you the solution to this right now. And then we're going to show that it does solve this. All right, that's all I'm going to do. So I'm here to tell you that the solution to this equation, this differential equation, is this. The solution is y equals t over rho gravity, and then cosine hyperbolic of rho gravity x over t. So now you get to work. What I want you to do at this point is I want you to verify this is true. So what that means, well, can someone tell me what I mean when I tell you I want you to verify that that solution works? Okay, so take the derivative, actually take the second derivative, take the derivative twice, okay, and get something. And then ask yourself if it's equal to this. So take the derivative of that twice, write it down, box it. Then take the first derivative of that, plug it in here, square it, add 1, square root it, multiply it times that. Box that, and these better be the same. Understand? You're gonna try and make sure that this side equals this side. Work together. You've got, well, 22 minutes if it takes that long. You know what you're trying to do? Take your time. Remember, T, rho, and G are constants. Constants always just come for a ride, right? As long as they're attached to the function. The only variable in the problem is x. All right. Have fun. I'll come around and check on you all in a few minutes and just see where you are. Make a friend. Meet your neighbors.